So hello everyone. So right now I am in Estonia, as you have been telling, and there was recently a proposal for making a project, and this project will involve a strong collaboration with the Latvia University, to which I will work at soon. And this work is kind of a jump from astrophysics and all that you do, spectral analysis, and all this kind of instrumentation, back to the rock, back to the geology, and also with a strong influence of shock physics and shock metamorphism. And through this presentation, you will see where I'm going through and what is the project about and what is this collaboration about, and this link that might be developing between astrophysics and geology in general. So this work, this project I am working on is mainly associated with asteroids and meteorites. And of course, where my work starts is from the main belt asteroids. And there was some talks yesterday or today about detecting asteroids and so on. And one particular event that was very impressive, it was in 2013, was the Chelyabinsk meteorite right here. You see a little video, and it was unannounced, and but what is nice is that we recovered a lot of this material. And what recovered are meteorites of stone type, are ordinary chondrites, and usually ordinary chondrites, like here on the left, usually look bright. And here you already see that there will be some speech about the spectral properties. And so in general, they are looking bright, but in some instances, they can look dark. And this darkening is caused by several factors, by melting of the wall rock, or by specific melting of individual phases like iron sulfides. In that case, what you see here is the light version of the Chelyabinsk meteorite, and on the right side is the dark version of this Chelyabinsk meteorite. And here the case is, here we have backscatter electron microscope images of thin sections of these meteorites. And on the left, you see all the bright spots. It is mainly made of iron sulfides and iron particles, like iron nickel particles. And what happens in this dark lithology is that all these iron sulfides elements and part of this iron nickel element, they start to melt, and they start to spread in between cracks of silicate mineral. And so it makes it dark, optically dark, because metals and iron sulfides are, by essence, they are dark, they are opaque to the natural light and also the cross-polarized light. What it does, and it is the main question of this project, is that it affects a lot the spectral properties of these bodies, of these meteorites, and in extent of these asteroids, because this light lithology that it appears lighter than the dark one, of course, they have a spectral reflectance that are associated with S-complex asteroids, and S-complex asteroids are one of the major group of asteroids in the main belt. But the dark lithology, which is still on an ordinary chondrite and which is still part of the S-complex asteroids, they do have a reflectance spectra that are looking like C-complex and X-complex asteroids. C-complex asteroids contain the carbonaceous chondrite, and X-complex asteroids contains the metallic meteorites, iron meteorites. And the problem is, the question we can ask ourselves is how much of these meteorites, of these asteroids, are actually darkened by shock processes or other space weathering processes. My project in itself was to understand how this iron sulfide melts through shock. And it's kind of basic principle. So we have like to start with some silicate background with some iron sulfide particles. Then you have the shock wave, which creates an heating of the elements up to 40-60 GPa shock waves here. And this heating of elements through heat diffusion and fracturing, it makes it so that this molten iron sulfide starts to spread through the cracks. My project is going further than that, and my project shows that there is many ways to make this spread of metallic elements. So this is the basic, what is shock darkening? This is a shock event from shock wave to melting of elements. And my research was mostly linked to numerical modeling with the ICL code. ICL code is also capable of doing impact modeling, for example. I also did some heat diffusion numerical modeling, shock recovery experiments were done, and melt experiments where I could spread this iron sulfide within the rock. And this is an example here of what are those shock experiments. Here you see that this zone with the particles, it is made of iron sulfide and metal, and the gray area is mostly made of silicate. And you see the shock wave going through this layer of silicates and particles, creating also a rise in temperature. So this is one part of the things of this the research I've done. A second part was studying shock recovery experiments. So you have a very thin layer of samples, this orange layer, which is shocked by explosives that are sitting on top of steel containers. And recently we have made some experiments. I will not go through this one too much in detail, but we did place this iron sulfide trolite inside some normal rocks, and we shocked this steel case where there was a sample, and we recovered the sample, and we are currently analyzing that. And here is an example that you can also study these shock experiments through shock wave modeling. And on the left, you see the shock wave propagation and the pressure that are applied. And on the right, you see the maximum pressure that have been involved. Here, this layer that is surrounded in green, it is the sample, and around it is the steel. So this is just to show you how these models works in general. And the experiment that I've been doing in Tartu University is that I took these rocks, dunite rocks made of silicates, olivine in most part, and we filled them with this iron sulfide here in tiny holes. We put them into some oven flushed by nitrogen at 1325 degrees. And what happened to these rocks? They actually darkens, like we see in the meteorites. We have the light meteorites, we have the dark meteorites, and here we have the light dunite T blank, and we have also all the dark dunite darkened by this iron sulfides. And what I want to do with at the Latvia University is to mainly develop a more concise review of this process. First of all, I want to do in the future several shock experiments, but it needs a lot of benchmarking, a lot of numerical modeling. So this is one first goal, is to strengthen this knowledge of numerical modeling and their use to understand shock experiments and best prepare these shock experiments, because shock experiments are extremely expensive. One shock experiment is 3,000. And when you are a lone researcher and you want to have many shock experiments, then you need to have this huge funding from different bodies. So you need to be sure that your experiments will be workable, will be feasible, and so on. The second part of my project that I have and I plan to propose to the university is to understand better these spectral properties and spectral analysis, and also to strengthen my own knowledge of astrophysics and spectral properties of planetary bodies in general, because this is something I like. I am a geologist and I want to strengthen my knowledge behind the border of geology and shock physics and go a little bit more to astrophysics. And this is why this work is kind of supported by Arnold Ubelis and Bernard Point. And I hope it will go well on that level. And also the third goal of this project is to strengthen my knowledge and the general knowledge for scientists around me on shock darkening, because shock darkening is extremely complex phenomenon, and I would like to be able to create a review of this process and to say finally how it works, because there is a lot of misunderstanding. there is a lot of good understanding as well, but everything is everywhere in little clusters, and I want to join that at one. And I think with the expertise of people who have been working long time in science, I will be able to pull up some reviews of this shock darkening process. And so in general, it's just to review this process and then to bring a little more attention to the distribution of asteroids in the main belt and tell, be careful, these asteroids have spectral changes. A lot of people have been telling that, but I think it must be emphasized more and more and more, because we are going through the future, and in the future it means that we'll have more and more visit to asteroids. Probably, you know, it's kind of science fiction today, but we never know. So it's kind of a alarming little message that says, guys, there's so many processes, and be careful with the data you receive from the main asteroid belts, because these asteroids are so small that it's hard to just recognize them only with spectral changes, spectral absorbance spectra. And here is just a little, this is all the papers that I've been kind of working recently. And here's a list of what I've been doing as well. So I hope that this project will be bearing fruits, and that the collaboration between Tartu, because Tartu has a lot of things to offer as well, and Latvia University will be stronger, and also between Latvia Astrophysics Department, Astrophysics or Astronomy, sorry if I make a mistake there, and the Geology Department also of Latvia University, because these links are a little weak, and I want to try to do my best. So thank you for listening to me. I hope I didn't go over the 12 minutes. And if you are up to questions, please ask them. Thank you.
Thank you. Now questions. Nancy?
One question. When the changes happened initiated by high pressure, which was obtained as a result of this explosion, do you see only structural changes or also chemical reactions?
We have tried to test a little bit on the chemical composition of this meteorite, and there is absolutely no chemical changes. So there is the same isotopic marker. This is the same compositional marker of the different mineral phases. What only changes is their phase. They just melt, and it's really only on spectral changes that there is something happening. But otherwise, there is nothing happening on the chemical level, nothing happening on the, how to say, not the spectral level, but like the phase are still there. They do not change. There is no change at all where witness is. And this is the most interesting part of this project, is there is no chemical changes. But there might have been in the past, because when you have primitive meteorites, you might have these kind of events where iron sulfide do melt in that way. And in the past, before it was equilibrated meteorites, it might have a lot of different chemical change at this point. So I'll try to also study that using these earth rocks. I have seen some chemical changes that were not observed in meteorites. So this is kind of it's in these meteorites, darkened meteorite, there is no chemical changes.
Thank you. Martin, please.
Very interesting talk. Talking about the dangers from space. I think at the return of Halley's Comet, not the latest one, but the one in the beginning of last century, there was some panic on the world because they realized that the Earth would pass through the tail of Halley's Comet, and they had just detected C-end radicals spectroscopically there. So would this be the end of the world? Are there any real dangers, of course, direct impacts and so on, but indirect, talking about chemical transformations or gas emissions or polluting the atmosphere? What is the current status of thinking?
In my case, I'm working mostly on the stony meteorites, and the stony meteorites are practically chemically I will not say inert, but they do not bring any kind of toxicity to the atmosphere, because and comets, I am not sure more about comets because comet it's not really my field, so I cannot really answer that question. But about the stony meteorites or the metallic meteorites, the bigger danger is that just they do impact Earth. That's I think that's more worrisome than the chemical change they might provide. And with Chelyabinsk, the most damaging things that happen were all these windows exploding and people being hurt by it. But there was no traces of chemical changes in the air and from the blast in the atmosphere.
Thank you.
More questions? Oh, okay, thank you once more.
Thank you.
And now the